What specific problem does the new method or algorithm aim to solve?
The new method or algorithm aims to solve the problem of identifying the essential components of optimization algorithms that facilitate both performance and stability in training autoregressive language models. The study focuses on comparing the stability to hyperparameters of various optimization algorithms, including SGD, ATOM, Lion, and Attafactor, across different model scales and architectures. The goal is to understand the role of preconditioning in adaptive optimizers like ATOM, and to determine if simpler optimizers like SGD can achieve similar benefits with minimal modifications. The study investigates the necessity of adaptivity for different parameters of the network and aims to provide insights into which parts of the network require adaptive optimization techniques for optimal performance and stability.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method works by first conducting a comprehensive sweep for training autoregressive language models across different optimizers, hyperparameters, architectures, and scales. The study aims to evaluate the stability and performance of various optimization algorithms, including SGD, ATOM, Lion, and Attafactor, across different hyperparameters. The experiments start with hyperparameters recommended by previous work and perform a learning rate sweep to identify the optimal learning rate for each algorithm. After determining the optimal learning rate, one-dimensional sweeps are conducted for other hyperparameters. The study focuses on the stability of optimizers with respect to various hyperparameter choices, such as learning rate and momentum. The results show that multiple optimizers introduced after ATOM demonstrate robustness comparable to ATOM and superior to SGD. The investigation extends to exploring the essential components of these optimizers that contribute to performance and stability. By studying simplified versions of these algorithms like Signum and Adelayer, the research aims to understand the role of preconditioning in achieving stability and performance. The study reveals that adaptivity is crucial for the last layer and layer norm parameters, while the remaining parameters can be trained effectively with SGD. Additionally, the research delves into the behavior of Adelayer and its variants, showing that adapting parameters of the last layer and layer norm parameters is essential for stability and performance. The study also explores the possibility of training most language model parameters with SGD, highlighting the importance of adaptivity in achieving optimal performance and stability. Through empirical investigations and ablations, the research provides insights into the key factors influencing optimizer stability and performance, ultimately shedding light on the fundamentals of optimization for language modeling.
What are the theoretical or practical benefits of using this method?
The theoretical and practical benefits of using the method described in the paper include the discovery that various optimizers, such as Lion and Attafactor, demonstrate robustness comparable to ATOM and superior to SGD. This finding challenges the prevailing notion that ATOM should be the default optimizer for training language models. The study also reveals that signed momentum, Signum, and a layer-wise variant of ATOM called Adelayer can recover the stability and performance exhibited by ATOM, indicating that simpler optimizers like SGD can achieve similar benefits with minimal modifications. Additionally, the research shows that adaptivity is primarily necessary for the last layer and layer norm parameters, while the remaining parameters can be trained effectively with SGD. This insight provides a more nuanced understanding of the role of preconditioning in adaptive optimizers and highlights the importance of adaptivity in specific network parameters for achieving optimal performance and stability in training language models.
How is the method validated or tested?
The method is validated or tested through a series of experiments that involve sweeping over hyperparameters, such as learning rate and momentum, for various optimization algorithms, including ATOM, Attafactor, Lion, Signum, and SGD. The experiments are conducted across different model scales, 150 meters, 300 meters, and 600 meters parameters, and transformer architecture variants. The results of these experiments are presented in figures that illustrate the performance and stability of the optimizers under different hyperparameter settings. Additionally, the study includes ablations and investigations of simplified versions of the algorithms, such as Signum and Adelayer, to understand their impact on stability and performance. The experiments also involve comparing the performance of Adelayer with a corrected version called Adelayer *, to analyze the importance of adaptivity in different network parameters. Furthermore, the study explores the role of preconditioning in achieving stability and performance, particularly focusing on the last layer and layer norm parameters. The experiments involve training models with different combinations of optimizers and hyperparameters to assess their impact on stability and performance. Overall, the method is validated through empirical studies, comparisons, and ablations that provide insights into the stability and performance of various optimization algorithms for training autoregressive language models.
What results were achieved with this new method?
The new method achieved results that showed multiple optimizers introduced after Atom, such as Lion and Adafactor, demonstrated robustness comparable to Atom and significantly superior to SGD. The study found that these optimizers exhibited similar performance and stability across different learning rates and multiple model scales, 150 meters, 300 meters, and 600 meters parameters. The research challenged the prevailing notion that Atom should be the default optimizer, as no single algorithm emerged as a clear winner in terms of performance or hyperparameter stability. Additionally, the study investigated the stability of various optimization algorithms across different hyperparameters, architectures, and scales, showing that, except for SGD, these optimizers were comparable in terms of both performance and hyperparameter stability. The results also revealed that Signum, a simplified version of Lion, recovered the stability and performance exhibited by Atom, aligning with recent work suggesting that the primary distinction between SGD and Atom is driven by Atom's resemblance to Sine SGD. Furthermore, the study empirically demonstrated that Adelayer, a variant of Atom that performs preconditioning on a per-layer basis, nearly recovered the stability and performance of other optimizers in previous ablations. Through empirical studies of Adelayer and its variants, the research showed that adapting the parameters of the last layer and layer norm parameters in a transformer is necessary to achieve stability and performance, while the remaining parameters could be trained with SGD.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the method outlined in the paper include 1. Limited architecture decisions. The study only ablated a few architecture decisions due to computational constraints, which may restrict the generalizability of the findings to a broader range of model architectures. 2. One-dimensional hyperparameter sweeps. The method only considered one-dimensional sweeps for hyperparameters, potentially overlooking interactions between hyperparameters that could impact the performance and stability of the optimizers. 3. Fixed batch size. The study fixed the batch size, which may not capture the full range of effects that varying batch sizes could have on the performance and stability of the optimizers. 4. Single dataset. The study was limited to language modeling with a single dataset, which may not fully capture the variability in performance and stability that could arise with different datasets and tasks. 5. Optimization focus. The study primarily focused on optimizer choice as a point of intervention for efficiency, potentially overlooking other factors that could impact the overall training process and model performance. 6. Computational constraints. The method's computational budget limited the exploration of 2D interactions between hyperparameters, which could have provided a more comprehensive understanding of the optimizer's behaviors. 7. Limited scope. The study's scope was restricted to investigating optimizers for language modeling, which may not fully translate to other domains or tasks where different considerations could come into play. 8. Hyperparameter sensitivity. While the study explored hyperparameter stability, the method's approach may not fully capture the nuanced effects of hyperparameter interactions on optimizer performance and stability. 9. Generalizability. The findings may be specific to the models, datasets, and hyperparameters tested in the study, and may not be universally applicable across all scenarios. 10. Intervention point. The study suggests that optimizer choice may not be the optimal point of intervention for efficiency, indicating that other factors influencing model training and performance may need to be considered for a more comprehensive understanding.
What future work do the authors suggest?
The authors suggest several avenues for future work based on the findings of their study. They mention that exploring interactions between hyperparameters in a more comprehensive manner, beyond one-dimensional sweeps, could be an important direction for future research. Additionally, they highlight the need to investigate the role of preconditioning for adaptive optimizers in achieving performance and stability in more depth. The authors propose further examination of the adaptivity needed for different parameters of the network, to determine if simpler optimizers like SGD can achieve similar benefits with minimal modifications. They also recommend exploring the impact of higher momentum values on optimizer performance and stability. Furthermore, the authors suggest investigating the behavior of different optimizers across a wider range of hyperparameters and architectures to gain a more comprehensive understanding of their effectiveness. Lastly, they mention the importance of addressing the limitations of their current study, such as exploring a broader range of architecture decisions, conducting multi-dimensional hyperparameter sweeps, and considering different datasets beyond language modeling.